Hi,
There
it's
has
Mr.
meat
Anderson, and
here.
today I'm going to
Look
be
here
talking
all
about
over.
physics.
There's the meat. How can
Physics
it
comes
choose?
from a Greek word,
Who's going to be
physis,
attacking
which
me?
just means
There's
nature.
our
And so
moon.
you could argue that
Yeah,
physics
their
is the
moon.
oldest
Everyone's
science that
right
we
here.
have.
I know.
Because the
Isn't
first
that
time
great?
somebody looked up at
There's
the moon
my
and wondered
friends
why the moon goes
actually.
through its phases,
I
they were doing
know.
physics.
Isn't it
And
right?
so it's been around thousands of
I
years,
think
but
what
it
is
really didn't
actually to
become
do it
quantified until we got to the scientific
is what we
revolution.
have over.
One of the big
There's the
names is
boys,
Galileo
girls, there's
Galilei.
male and the
Again, he
female.
really was good at using
Everyone's
the telescope and
Emily
made some
beats off
amazing
Alice.
discoveries as far as
You
space.
chose your
But he
pointed.
also
Your point.
did some
There's
studies in
Alice and
mechanics,
Anna
or in
there's Anna
kinematics,
and
or
Alice.
how objects move.
Looking
He
for everyone.
probably
Alice
didn't
for
drop
one for
those
Anna
objects
here.
from the
And
leaning
Alice is for Anna is.
but he did do some cool experiments on pendulums, and so let me show you an example of what he did. I'm using software called Fun. Fun is a physics simulator, and it actually is a lot of fun. What you can do is build objects, and then you just hit play, and then those objects will start to move. And so that's a simple pendulum, one similar to what Galileo was actually studying. And so let me move back for a second, and let me make another pendulum over here. And one of the first things he discovered is that when you had two pendulums, we'll say the one on the left and the one on the right, and the one on the right has a longer length, that one's actually going to have a longer period. In other words, the time it takes to swing back and forth. He also found that no matter what the object's weight is, they had the same pendulum.
What's it
And so
here?
he was starting to figure
What
out
the
this
heck is
idea,
your hand? I know.
at least
Isn't it
that all
right?
objects
You're
seem
talking
to spin,
about
if not
that's
fall,
great.
at the same rate. So let me get some of these and clear this off. And now we'll go back and talk a little bit about the next scientist and his name.
My friends here, come back.
Isaac
there's
Newton
some
came
men.
up with
How can
three
it you
theories,
now?
or
Hang
three
on, every
laws, and
kid.
you've probably
You're
heard
ever.
these before.
I know.
First one is the idea of inertia, and you've maybe heard it this way.
How come
That an object at
here?
rest tends to stay
This
at
is
rest, an
getting
object in
delicious.
motion tends to
They
stay in
never
motion,
did
so we call that his first law. His second law could be summarized as
Hallucinations. We
this:
collection
force
everyone
equals mass
before.
times acceleration.
One has
And then the
only has
last
been
one
here.
is this idea that for every
At
action,
one
there's an
years,
opposite and equal
degrees
reaction.
school.
And so we call
Families.
those reaction
Research.
pairs is a good way to say
Like
that.
that you have to do research from school.
In other words, when I
Fire
push on
school
a wall is pushing
Isn't it right?
vertically on me. And so let's jump into the virtual world and take a look at
All
how
right.
those would work.
There.
First of all, let me add a ground for just a second.
Okay, no problem.
And so now I'm going to add, let's see, let's go back, actually. So let's add a ground, and now let me add an object. So for just a second, so if I add a ball like this and hit play, that object is going to fall like that. If I rewind it for a second and I lose gravity, so there's no gravity and I hit play, what's going to happen? If there's no gravity and I hit play, that object is now at rest, and so it's going to stay at rest. Once I add gravity to it, it's just going to fall. Now if I time it right, again, I had it bounce, and then I got rid of gravity, and it just kept going in that direction. If I add gravity again, it's just going to fall all the way down. And so that's Newton's first law. An object in motion stays in motion, an object at rest is going to stay at rest. And if you're paying attention down here, this object is starting to move up because I've got rid of gravity. So make it step down to the end. Okay, what was Newton's second law? Newton's second law, remember, is that force is equal to mass times acceleration. What does that mean, F equals ma? Well, it essentially means that if you apply a force to a small mass, you're going to get a huge acceleration. Or if you apply a force to a huge mass, you're going to get a small acceleration. So let me give you an example of that. Let's bring in a catapult. And so if I bring a catapult in like this, and hit play, catapult's going to throw that object. Oops, I got rid of gravity for a moment. So it's going to throw that object in the other direction, like that. Let me rewind that for a second. And so what I can do is I can grab this little object right here, and I can change what it's made up of. And so let's change its mass. And so now let's not have it be a mass of 60 grams. Let's make its mass be much bigger, like 1.5 kilograms. If I throw it again, it's not able to throw it. So what again I've done is I've increased its mass, and so its acceleration got slower. Well, let's try and find something in the middle. Let's find a mass that works. So something like that. And so that would be Newton's second law. In other words, as you increase the mass of an object, that object is going to, its acceleration is going to drop off. Now, one thing you should have seen when we did that is don't take a look at the object this time, but let's take a look at the catapult. What happens with it? Did you see that? So when the object goes to the right, in this case, then the catapult goes in the left. And so that's Newton's third law of motion. For every action, there's an opposite and equal reaction. Now, why did the object go farther than the catapult? That goes back to Newton's second law. Well, I'm getting into a lot of physics, and physics that we'll actually deal with later. But the reason I'm doing all of that is that I want you to understand that physics, once we started quantifying, we came up with these laws, it never changed. In other words, for the next 200 years, once we had Newton's laws of physics, that was it. And in fact, in our book, the physics that we cover is just Newtonian physics. And so what do I mean by that? Well, mechanics, so we're just talking about one specific type, or one part of physics. Mechanics, and all we understood about mechanics dealt with just this box down here. And so, if we look at the size of objects, so right here I'm going from size of objects down at the level of an atom, so this would be an atom down here, up to the size of a planet. So if we go from very small to the very big, classical mechanics and Newtonian physics only works if you're dealing with big objects the size of me.
Does science have me a speed here?
But when you get down to the level of an atom,
nobody touched that.
Speed is another thing. So if we go from speed where we're not moving, or moving as a bicycle, and then we move up to the speed of light, the rules tend to change as well. And so physics is a really broad science. But we didn't start to understand this until we started to get some people. And so Einstein was the first person to start to explain what happens to objects, not just swinging on a pendulum, but as they start to move really fast and as they move towards the speed of light. And he found some really crazy stuff. Like as you start to approach the speed of light, time will actually slow down. In other words, you could travel away from here at the speed of light and come back, and you and I are going to be a different age. We also had, this would be Max Planck, but a lot of scientists came up with this idea of quantum mechanics. Quantum mechanics is kind of explaining what happens at the atomic level, where we start to get this duality, where it's not only a particle, these small objects, but they're
what's that supposed to mean?
And then finally, we have this, in this last century,
okay, let's think of her.
Again,
what you hear? Look at your all over place here. No, that's enough. Alright, you're alone. Okay, let's see her. I might have her alone. That's enough, kid. Okay, that's enough. You're in the room. Not so fast, kid. Not so fast, kid.
What I want you to understand is that classical mechanics or Newtonian physics is really what we're going to talk about for a lot of years in physics. But it's just one thin slice of the pie. And even with that, mechanics is one thin slice.
No, I guess not.
Physics, so we're going to deal a lot with kinematics, like acceleration.
But Alice and Anna here alone.
But there's a whole other group of physics in physics called thermodynamics, where we deal with things like heat.
Goodness, looking here
alone. There's another group where we deal with electromagnetism.
Actually,
we deal with things like electricity and magnetism.
Sorry, I'm late.
And so, I'm leaving some things off. Physics
I'm here,
also is made up of a lot.
And release that me alone. And by we are all of us.
And so there's a lot to physics, but what I want you to understand is that physics is simple to understand.
Or not, test me alone.
And if you understand that, you've taken the first step. And so I hope that's helpful.